Hello everyone. In previous video we have seen the classification and types of algorithm and the nomenclature for scheduling of hydrothermal power plants. Today in this video we'll discuss about the first algorithm, that is algorithm for hydrothermal scheduling. That is the first one, that is scheduling based on energy. So we'll discuss today about scheduling based on energy. So this method can be used in systems where the hydro generation is a major component, but it cannot meet the demand. So in order to meet the demand, the thermal generation has to be included. So it's a combination of hydro and thermal. So let us consider a system where we have one thermal and one hydro plant to supply the load. So let us consider the system with the one thermal and one hydro plant to supply the load. So this can be given as a P load or P demand. So now this is a thermal plant. So the deciding factor or the constraint here is actually the cost. So F is cost function. So for thermal power plant, the constraint is basically the cost of operation, or which can be given by a mathematical formulation which is nothing but cost function. This we have seen in scheduling of thermal plants. So F is a cost function. So H is hydro plant. So constraint for this hydro plant is nothing but the water discharge. So water discharge. So we have seen the water discharge can be given as Q, or in some textbooks the notation is a Q naught. So water discharge is a main constraint. So we can take the power generated by hydro plant as a PGH, or PGH in nomenclature we have seen PGH is a generated or power generated by hydro plant, and PGT is nothing but power generated by thermal plant. So this is a system where we have one thermal plant and one hydro plant, and all these nomenclatures we have seen. So P load is nothing but the demand, power demand. So in order to write the algorithm, initially we have to make some assumptions. So the first assumption is the hydro plant has the capacity to supply the entire load by itself. So entire load which is given by P load can be supplied by the hydro power plant alone. So this is the first assumption. Though there are two plants, one is hydro and one is thermal, the first assumption what you are taking is the entire power load, that is P demand, will be supplied by the hydro plant. So what we can write from this is the maximum PGH what we have, maximum PGH in any interval, PGH value will be always greater than the demand value or the load value. I can take it as load or demand. So this is same as PD. So I can write this as PD also. So, or I'll write one more equation or constraint. So this is PGH K is PD in K, this or this. Okay. So that is because I have taken P load same as PD, where PD is the representation for power demand, P load is the same. So the hydro plant has a capacity to supply the entire load by itself. So hydro plant alone can supply the entire load. So where K you can write 1, 2, 3. I have told in the previous video, K is nothing but integer value which is a particular interval. So we have n number of interval, the entire time period can be splitted into different intervals. So in any particular interval, the maximum PGH will be always more than PD. That is an assumption. So if it is more than this, the demand can be supplied by entire demand can be supplied by PGH alone. So the second assumption is nothing but the energy from the hydro plant is not sufficient to meet the load all the time. See, please understand this concept. See, in the second assumption, they have taken the energy, and here we have taken the assumption for capacity. So when I say capacity, it is the power. That is what we have mentioned here, PGH. So power capacity, the maximum power capacity is such that it can load it can supply the entire load. But if suppose I take the energy is basically a product of power and time. So if I take power in particular time or for a period, it is not sufficient to meet the load. That is because the hydro plant will have a constraint on water discharge. So that depends entirely on the season and the availability of water. So the energy from the hydro plant is not sufficient to meet the load all the time. That is without the thermal support. If suppose there is thermal support, there may be energy which is sufficient to supply the entire load. So please understand these two assumptions. So for this, what we can write is summation K is equal to 1 to N PGH K HK. So this is nothing but energy. H is for hour. H is the number of hours in a particular interval. So this will be actually less than summation K is equal to 1 to N PD, where PD is a P load HK. So okay, so this is the second assumption. So I can write where HK is the number of hours in interval K. In interval K. So remember that interval is not just 1 hour period. So interval, each interval can be it's for many hours. So we have n number of intervals and each interval is for many hours. So in one interval, say suppose kth interval, how much is the number of hours? That is given by HK, and H into P gives you the energy, and this energy is more than this energy. So this is the second assumption. And also what we have is summation, from this summation K is equal to 1 to N HK is nothing but T max. So if I take summation of all the time number of hours, that gives me the maximum time what we have. So that is T max. So third assumption is nothing but the energy required from the steam plant is given by, so E is equal to, that is energy to be supplied by, so I can take the as E as energy to be supplied by thermal or steam, both same. So this is given by, so we have written here previously. So this is energy for hydro and this is the energy required, that is the load energy required or energy needed, so demand needed. So what we can find out from these two mathematical formulation is the energy to be supplied by thermal. So how to write, since the demand energy is according to our assumption it is more, I can write minus summation K is equal to 1 to N PGH kth interval HK. So I can write whatever after subtracting this energy from the demand energy, we can get energy to be supplied by the thermal. So this is energy demand. From this I can write here energy demand, and this is nothing but energy supplied by hydro plant. So these are the three assumptions what we have to remember. So now from this what we can write, E is nothing but similar to this format, let me write. So E is nothing but summation K is equal to 1 to N Pgt K Hk. So this is for thermal. I can replace here E by this term. So also we have summation K is equal to 1 NT. What is NT? NT is nothing but the time intervals for which, number of time intervals for which thermal is on. We have seen in the previous video, that is the nomenclature. So N is the total time intervals, number of time intervals. NT is the number of time intervals for which thermal is on. So for this it is, sorry, here I have to write NT. So this is HK. If I take only time for this duration, I can write this is less than T max. So this you can take TT. We have represented this by TT. So this is nothing but TT, and this TT will be always less than T max, because the remaining we can write T max will be equal to TT plus TH, where TT is the time period for thermal power plant and TH is for hydropower plant. So this is regarding the assumption. Now let us do the analysis. Now what we have to write here is a problem statement which can be written in a mathematical format, and this has to be basically done to minimize the production cost of thermal power plant. We know the production cost is more for thermal power plant compared to hydro. So what we need is basically minimization of the thermal production cost. The problem is to minimize. So we have to form a mathematical model. Production cost. So this is actually very important, the mathematical formulation. So let me write. So main aim is to minimize. What to minimize? Production cost. So production cost of thermal can be given by Ft, which is actually written as production cost for all these intervals, that is from 1 to NT. Why I have taken NT? Because the thermal power plant is on only for NT intervals. So from 1 to NT, and which can be given by the energy, which is nothing but this. So function, it's a function. What function? It's a cost function. Remember, it's a cost function or production cost function, and we have constraint. So always when we formulate mathematical model, we have to write what we have to exactly do, whether we have to maximize or minimize. Here anyways it has to be minimized. The production cost has to be minimized, which can be given by this equation. And what are the constraints? So constraint what we have is, so K is equal to 1 to NT Pgt K minus Pgt K Hk minus E is equal to 0. So this is a constraint. So where, what is this E? E is nothing but, we have written, E is nothing but combination of this demand minus the hydropower plant energy. So E is nothing but, or you can write in place of E this. So where E is equal to, you can write summation K is equal to 1 to N Pd K Hk minus summation K is equal to 1 to N Pgh K Hk. So we have written mathematical model So here actually this is known as mathematical model. So what we are doing basically is minimizing. So in mathematical optimization problem, so optimization is either we have to make less or we have to make more, that is optimization. So since it is cos function, so we have written, say for example in this mathematical model or in this algorithm, what we are doing is we want a minimum cost. So it's a mathematical optimization problem in which we need minimization, that is why we have written minimizing. So this is actually the basic problem and we have to write the constraint. So this method is known as Lagrangian method. So in mathematical optimization, the method of Lagrangian multiplier is a strategy for finding local maxima or minima subject to a constraint. So we can write now Lagrangian function as, so let me write the Lagrangian function for this mathematical model. So using Lagrange's method, we define Lagrange's function. So remember how to write the Lagrange's function. So let me denote it by L. So whatever mathematical model you have written, that is the optimization statement, this one. So let me write this is equal to summation k is equal to 1 nt pgt k hk. So this is a statement what we have written plus lambda. So lambda is a Lagrangian multiplier we say into the constraint. So constraint I can write E minus. So let me write this. I can write the same statement as, if I take it to other side, that becomes E minus this, because I don't want summation here, that is why I am writing like that. So summation k is equal to 1 to nt, the same thing, constraint E minus this term. So pgt hk. So remember how to write the Lagrangian function. So L will be equal to the basic optimization statement, that is this, plus Lagrangian multiplier and the constraint. So this is the Lagrangian function. So now to minimize the function, we take a derivative and equate it to 0. So to minimize the function, take derivative of this Lagrangian's function and equate it to 0. So let us take the derivative of this, and since it is a multi-variable, many variable dependent function, so let me take partial derivative. So partial derivative of this with respect to PGTK, so with respect to thermal power plant power, will be equal to, so this is a function which depends on only this. So I can write differentiation, I need not write partial derivative here. Why I have written partial derivative here? Because this function depends on both PGT and E. E is function of PGH also, that is why I have written partial derivative here. Now for this, while taking derivative of this, I am writing only this, that is derivative. So function of PGT k with respect to dPGT k minus, and this is lambda. So E is 0 minus this is I can write differentiation of this with respect to PGT gives me 1, whereas this is a constant, this is anyways constant. Why? Because this depends on PGH, but here we will be differentiating with respect to PGT. So this is 0, I can write minus, and this is 1. Sorry, this is plus. is equal to 0. We have to compare it to 0. So, this one. So, I can forget this part. So, this equation I can equate it to 0. So, what we have is differentiation of cos function, where cos function is made up of thermal power and it is with respect to Pgt k minus lambda is equal to 0. Or I can write differentiation of f Pgtk. This is not power, this is the time interval, dPgtk is equal to lambda. So, we have written a Lagrangian multiplier function from this. So, this is incremental cost. So, this is incremental cost. In general, we call lambda as Lagrangian multiplier, but particularly for this algorithm, we say this is incremental thermal plant cost function. So, it is a incremental cost. Now, what we need is the thermal power plant must run at a constant incremental cost for the entire period during which it is on. So, let me write in a graph pattern. So, let me take this as time scale and this as power scale. So, where we have demand here. So, this is PD, the maximum demand or the load, P load, and with the constant incremental cost we have Pgt here. So, this is for thermal. So, this is the thermal plant and this is Tt and this is the Tmax, Pgt. So, whatever remaining power is there, that has to be supplied by hydro, and similarly for the remaining time period. So, this is Tmax and thermal is on only for this duration with this power generation, that is with the constant incremental cost. So, why I have written star is where Pgt is a thermal power generation, but with the star I have written for constant incremental cost. So, let me write here where Pgt star is a thermal power at constant incremental cost. I hope this is clear. Incremental cost. Now, we know that summation, we have written incremental cos function. So, now summation k is equal to 1 to nt hk is nothing but Tt, which is a total time for which thermal is on. Thermal plant is on. Now, total cost over the interval Tt can be given by the total cost over the interval Tt can be given by, so let me write total cost, which is Ft, which is equal to summation k is equal to 1 to nt function of Pgt, which is nothing but, now I will not be writing k over here because that for that particular instant it is, and hk. So, and with the constant incremental cost. So, Pgtk is replaced by Pgt star. So, this. Now, let me write this as f Pgt star, the summation sign I will take it here. So, this is k is equal to 1 to nt hk, and this is, so this Ft is total cost, whereas f function of PGT is a cos function. So there is a difference between ft and this. So this is a cos function. So let me write here, this is a cos function, and this is cost, total cost. So total cost will be always in rupees, whereas cos function will be in rupees per hour. So this now can be written as f PGT star, and this is nothing but we have written it as TT. So this equation has to be remembered, let it be. So this can be written as the same thing. Now I am writing equation for this. Equation for this can be written as in a form of a quadratic equation. This we have seen in power system analysis too, while studying scheduling of thermal power plants only. It's not a combination, just the thermal power plant only. While scheduling, we have seen this equation, that is A plus B PGT plus C PGT square. PGT square. Now since we have to use star here, let me write ft as, now the equation becomes ft will be equal to, I'll substitute this here. So here A plus B PGT star plus C PGT star square into this into TT. This into TT, where A, B, C are coefficients of cos function, where A, B, C are coefficients of cos function. So once again let me tell you, there is difference between ft and f of PGT. So ft is the total cost and the unit of it is rupees, where f of PGT is cost function and the unit is rupees per hour. So now total thermal energy can be given as, total thermal energy can be given by, we have written this previously, E is equal to summation K is equal to 1 to NT. See, E here I have taken for thermal energy. So PGT, or let me write ET, PGT star HK. So this can be written as PGT star summation, let me write it inside. So NT HK. So this becomes PGT star TT. So from this, what is TT? TT will be equal to ET, which is energy PGT star. So let me use E for the energy, because we have taken initially E as thermal energy. We have taken E as thermal energy, that is E is nothing but energy to be supplied by thermal plant. So let me take here E only. So here E only. So E is this. So let me take this as E. So this will be equal to, sorry, this is the equation. This is the equation. So TT is E by PGT star. Now what is FT? So let me substitute it here and this equation. So total cost. So FT, total cost, will be given by function of PGT star into TT, where TT can be written as, TT is E by PGT star, and also we have written cos function as A plus B PGT star plus C PGT star square into E by PGT star. So what we want actually is from this, so we have written a simplified version of cos function. Now what we need is a minimum cost, total cost. So for a minimum total cost of thermal power plant, so we have to differentiate the cost function with respect to Pgt star. So if I differentiate this, I'll be getting, see, you have first term as AE divided by Pg, or let me write that first, then we'll differentiate it. So Ft now becomes, AE divided by Pgt star plus BE plus CE Pgt star, because when I multiply this with this, it becomes AE by Pgt star. When I multiply this with this, Pgt gets cancelled, so we have B into E plus C, and when I multiply these two terms, we'll be getting this once it gets cancelled, Pgt star gets cancelled once. So what we have is CE Pgt star. So now we have for minimum total cost, I have to differentiate it. So Ft with respect to what? With respect to Pgt star. So with respect to Pgt star, so when you are differentiating this, you will be getting minus AEE divided by Pgt square, and when I differentiate this, it becomes 0 plus, when I differentiate this, it becomes CE, that's it, is equal to 0. So it's a minimization problem. So in order to find the minimum total cost, we'll be differentiating it and we'll be comparing it to 0. So take this now. So we have CE is equal to AE by Pgt star square. So this gets cancelled. So what is Pgt star square? It's A by C. So what is Pgt star? Is the square root of A by C. So we have written the scheduling of thermal power plant. So this equation gives the power, that is Pgt star, at which the thermal unit must be operated to minimize the total cost. The time for which the thermal plant must be run depends on the hydro energy also. So you can see here the power is not depending on time, it depends only on A and C, which are nothing but the coefficients of cos function. It doesn't depend on time, but the time for which the thermal plant must be run depends on hydro energy also. Okay, so this is about scheduling based on energy. Thank you.